This is algorithm 2 for matrix-matrix multiplication. The default matrix size is n equals 100, but additional command line arguments can change the n. The matrix is populated by random numbers from 0 to 9, and then we initialize MPI and get the com size and the processor ranks. The MPI request and MPI status variables are for a non-blocking send and receive later on. If the matrix size isn't divisible by the processor count, then the program will preemptively end. Then, in order to more efficiently send the matrices for messages, the matrices are turned into one-dimensional arrays. Matrix A is goes by row, and matrix B goes by columns. Then these partitions, these one-dimensional arrays, are scattered into local calc A and local calc B respectively. Then the processes begin their respective calculations. Once the calculation for the initial blocks are finished, the processes then send their rows to the next processes. It's a non-blocking send, so they don't care about what the next receive is, as well as a non-blocking receive. And then synchronize back up with MPI wait, and this will loop for however many process count we have. Once calculations are finished, all of the result matrices are gathered into local calc C, and then since this local calc C is a one-dimensional array, it'll be added into matrix C by column, and then that's the end of calculations. This is for validation, and then the final time is calculated, printed out, output, MPI finalize, and close program.
Okay, hello, my name is Clayton Glenn, and I'm here for CS4473. This is Intro into Parallel Programming, and I'm going over the Fox algorithm for matrix multiplication. So we have a default matrix size, and our debug is 0, but I went ahead and ran it with a debug of 1 earlier just to get us results and to show what we're going through. So this is just a little, it prints the array all nice and neatly in a matrix form, and we have our global variables, and then right here is where we create random numbers between -1 and 1. In that kind of fashion for both the matrices A and B. Then we just print it out, and then we initialize the MPI, and now we're running all processes at the same time. And so we create these local variables, and then if we go ahead and finalize if the square root of the processes does not divide by the number of elements, and then we go ahead and start our time. Now our master rank is going to go ahead and print out the size and processes just to make sure we're on the right path. And then right here we're going to partition in the matrix where each block goes to the correct process. So we want 0, 1, 4, and 5 to go to process 1, which it shows directly right here. And I'll show you that it's for process 2, process 3, and process 4. Obviously it will partition that in that way. So we do that for A and B, and that's just a simple little algorithm. And then we go ahead and print that out, and then create our local arrays that we're going to be holding all these values in for A and B. So we're going to go ahead and scatter, and then we're going to create a result matrix to collect all the results. And then we are going to use this algorithm right here as you see 0, 4, and 8. We will put that in the first row, and then 1, 5, and 6, and these will be indexes that we'll need in the future, but 1, 5, and 6, and then 2, 3, and 7. And then we're going to go ahead and broadcast the B elements that we need to all the arrays, and we're also going to bubble up the A arrays that we need. So that'll be this huge portion right here, all of this. And as we're doing this, we're going to multiply and then add to the resulting matrix. And that will end up giving us the correct resulting matrix at the end. And then we're going to go ahead and MPI barrier and then collect the time and then print it out. And then we're going to print the resulting matrix or matrices in the processes, and that'll end up lining up the way we need to. So I'm going to go ahead and show you the output, and this is the output that we have. So this is the original arrays. Here's A and here's B, and then it went ahead and printed 4 times. That was a little process mix-up I had on debugging. And then this is the arrays after the swap algorithm. So I'll show you. We'll take this in as an example. So 0.53, 0.75, 0.81, 0.81. You notice 0.53, 0.75, 0.81, and 0.81. That's our block that we wanted to shove in the first row. And that's exactly what it did. It did the exact thing that we needed, 0.78, or 0.12, 0.78, 0.82, 0.65, all that good stuff. So that went ahead and did what we needed it to do. And then I just have this for debugging purposes, the sending and receiving of A and B. And then we collect the total time elapsed, and this is the printed results that's after the Fox algorithm has already been implemented. This will be the first process, which will be the top quarter of the matrix over here, and then the second process will be this quarter of the matrix, third process this quarter of the matrix, fourth process this quarter of the matrix, and that will be the final resulting matrix for the whole program. Thank you.